Now we are going to look at more evaluation rules for our C++ like language, and we're going to first look at these rules that involve control flow. So far we have looked at straight line pieces of syntax, but now if my syntax or my abstract syntax tree has an if then else, so if E1 then E2 else E3, evaluated under a context which is formed by the current object, the variable environment and the store. Now what do you expect such an expression to evaluate to? So recall that in our language we say that the value that this expression if then else evaluates to is void. Alright, so the value is easy, but what about the side effects? Alright, and so to understand what side effects should be visible at the end of the evaluation of this if then else expression, basically what we need to do is first evaluate E1, and maybe the evaluation of E1 is going to have its own side effects, and then under the new context, which includes the side effects induced by E1, evaluate either E2 or E3 depending on whether E1 evaluated to true or false respectively. Okay, so that's what our rules are going to reflect. And so this is the first rule, which is called if then else true, and it basically says that you first evaluate in the same context S0 ES E1, and if it evaluates to Boolean value true and side effects captured in the store S1, then you evaluate E2 in S1. Because the value returned by E1 is true, we evaluate E2, and also notice that E2 is evaluated in the updated store S1. And so if E2 returns V comma S2, we just ignore the value V, because the semantics of our language are that this expression is going to return a void value. This was also discussed when we were discussing typing rules for our language. And so the value is void, we just ignore the value V, but the side effects are captured in the store S2, which are obtained after evaluating E2. And notice again that E2 is evaluated in S1. Okay, now this was for the case when E1 evaluated to true. We need a similar rule for when E1 evaluates to false, and that's not very different. We just change true with false here and E2 with E3 here, and everything else remains the same. So if E1 evaluates to false and its side effects are captured in store S1, then we evaluate E3 instead of E2 under the updated store S1, and if that returns S2, then that's the final store at the end of this evaluation. In both cases, the value is still void. Alright, so that's if then else. Now, just to contrast if then else with the ternary operator, recall that unlike if then else, the ternary operator actually returns a non-void value. So, can return a non-void value. So, let's say this is my syntax, E1 question mark E2 colon E3, where this question mark and colon represent the ternary operator. The meaning is very similar to if then else, except that this returns a non-void, this may return a non-void value, and it will return a value that is either E2 or E3's value. Recall that when we were discussing the typing rules, we used this operator called least upper bound, but here we are not going to use the least upper bound. We'll have the exact runtime value, because this is not a static analysis, this is not a semantic analysis, this is actually the runtime evaluation of these expressions. And so what we're going to do again is that we're going to evaluate E1 first under the same context S0 ES, and then if it evaluates it true and side effects are captured in S1, then we evaluate E2 under S1. Okay, and let's say it gives us V comma S2, then the final value is just going to be V comma S2. Alright, so notice that the value is no longer ignored. So the return value of this expression is V, which is evaluated through E2. And recall that E2 and E3 may be of different types, and that's perfectly okay. We don't really care. Now during evaluation, the dynamic type of this expression would be whatever is the type of E2. Alright, and without any regard to what is the type of E3. Unlike a static semantic analysis rule, which had to take the least upper bound because it had to conservatively cater to both the possibilities of E1 returning true or false. Here we don't need to be conservative. We just take the value whichever depending on which branch is taken. So the other kind of dual rule to this is instead of true you have false returned by E1. And so instead of E2, you now evaluate E3 under the updated store S1. And now whatever is the value returned by the evaluation of E3 is the value returned by the whole expression. And the store is also updated accordingly by first evaluating E1 and then evaluating E3 on the updated store. So the final store is S2. Okay, so that's ternary false. Now let's look at a more interesting rule, which is the while construct in our language. So recall that the while construct in our language looks like while some Boolean expression E1 and then some body expression E2. And the question is, what should be the rule for this? So first of all, just like if then else, a while expression also returns a void value, but it may update the store through side effects. And so there are two cases again, just like if then else. One case is when E1 evaluates to false, and the other case is when E1 evaluates to true. So let's take the first case, which is E1 evaluates to false, and we're going to call it while false. So if E1 evaluates to Boolean value false, and the evaluation of E1 updates the store S to S1, then the evaluation of the whole expression also evaluates to void comma S1. So we just ignore the false value and we just replace that with the void value and just return the updated store due to evaluation of E1. This is basically saying that, when you evaluate this expression, you first evaluate E1, and if E1 evaluated to false, then you just ignore E2 altogether, right? And that's the whole idea. And the result of evaluating this expression would be just void in terms of value and S1, which is in terms of the side effects store. And S1 is basically capturing the side effects that are induced by evaluating the condition E1 itself. Now, what about the other case? The other case is when E1 returns true, and that is slightly more complex case. So let's say E1 returns true, and so under the same context S0ES, we evaluate E1 and it returns true and returns a store S1 that capture the side effects. Now we need to evaluate E2, and then we need to again evaluate E1. All right, and in fact, the other way to think about it is that after we evaluate E1, if it evaluates it true, then we are going to evaluate E2, that's one iteration of the loop, and then we are going to evaluate the whole loop again, but in the updated store. All right, and so that's what the rule is going to be in our big step operational semantics. And so the rule is that you first evaluate E2 under the updated store S1, which was updated due to evaluation of E1. So you evaluate E2, and let's say E2 gives you a value V comma S2. Now the value is not so meaningful because the value returned by a while expression is just void. So we'll just ignore the value, but we're going to use S2, and in the new updated store S2, recompute the whole expression while E1 E2 again. And so I'm going to say S0 S2 under this context, if while E1 E2 returns void comma S3, then under the original context also the while E1 E2 returns the same values void and S3. So what am I doing here? I'm just unrolling one iteration of the loop. So I evaluate the condition for the first iteration, I evaluate the body for that iteration, and then for the rest of the iterations I basically just use this updated context with S2. And notice that the difference between this the rule before the inference line and the one after the inference line is only in the side effects produced by the body and the evaluation of the condition. Here the store is S2 and here is the store is S. All right, and so typically we write loops where we are updating a variable in the body and let's say checking that variable in the condition, and so those updates are getting reflected in S2, and so we can expect this application of rules to eventually terminate. Once again, recall that when we defined this evaluation judgment, we said that you should read it as if it terminates. So if it does not terminate, so for example, if I were to read this again, I'll say if the evaluation of this while loop terminates, then it evaluates to, under this context, it evaluates to void comma S3. And now if you read this whole rule, it makes sense only if you basically use the termination condition, this termination precondition, let's say, or antecedent. And so that becomes relevant in this case. Because if the loop was not terminating, then we cannot talk about such big step semantics, and we won't be able to give a value to while E1, E2 because it actually never terminates. Not even the void value. All right. Okay. Let's move forward. Declarations. So far our E hasn't changed at all. We recall that E is the variable environment that maps variable names to locations in the store. And what is the way for a language, a statically scoped language like C, C++ to update E? I would like to point out here that for dynamically scoped languages, E is updated even by just, at runtime. It's basically updated as and when you make new declarations, and those declarations can kind of travel in other functions and stuff like that. But we also, when we discussed scoping, we said static scoping is more popular, and so our language also supports static scoping and not dynamic scoping. And in static scoping, a new variable is declared by a declaration of this form in a new scope, which looks like T, which is the type, ID, which is the variable identifier that's being newly declared, and equals E1. And so just assuming that it's an initialized declaration. And so if I say T ID equals E1 and then I say semicolon E2, this basically means that I've declared a new variable and then I have the rest of the body for the to be evaluated under the new environment which has this new declaration in it. And so what do you imagine? Basically what needs to be done here is that this particular declaration should update E, right? So there should be an updation on E, and we should get a new E prime, and then E2 should be evaluated under E prime. Okay, and whatever E2 returns under the evaluation under E prime, the updated environment, that should be the value that is returned, including the store. All right, so that's what our rules are going to capture. So first of all, we are going to evaluate E1 under the same context as 0ES. So E1 is, during the evaluation of E1, we have not changed either the environment or the store. Let's say E1 evaluates to V1, S1. Then what do we need to do? We need to update the environment. So we need to update the environment before we start computing E2. And we don't know how to update the environment, so we're going to discuss that next. But let's say under the updated environment, E2 returns V2, S2, then that's the same value, store, that's going to be returned by this entire expression that includes the declaration. So now the only question that remains is that what should be the updated environment and what should be the updated store under which E2 should be evaluated. Okay, so informally speaking, basically environment should have all the mappings that E already has, plus it should have a mapping for ID to E1. If E already has a mapping for ID, maybe because ID was declared in an outer scope as well, then that mapping should be overridden by this particular mapping from ID to its new location, not E1 but to new location. We call that environment E maps an ID to a location. And then the store should also reflect this fact. So not only should store have all the side effects that are present in S1, but the store should also have written the value V1 at the location that ID represents, because that's what ID equals E1 is supposed to do. It's supposed to write the value evaluated by E1 into the location that ID represents. Okay, so to do this, we are going to, so these are the questions. In what context should E2 be evaluated? We need an environment like E, but with ID mapping to LNew, where LNew is a new location that will be created, and a store like S1 with LNew mapping to V1, where V1 is the value computed for E1. Notice that when we are saying that we need to update the environment with a new mapping, or when we are saying that we need to update the store with a new mapping, nowhere are we talking about whether this mapping is on the stack, on the heap, nothing of that sort. In fact, there's no notion of stack or heap. It's just a map notion of there are some maps. A store is a map and an environment is a map. And this is keeping things as abstract as possible so that implementations are free to choose whatever implementation they like for store and environment. Right? For example, typically they would use the stack as they would allocate local variables in the stack, or they would allocate non-local variables or global variables not in the stack, in the global data region and things like that. Something that we have already discussed when we were discussing runtime environments. Okay, so how do we represent LNU? Well, we want, the only requirement that we have on LNU is that, so we don't want to say anything about stack or heap or anything like that. The only requirement that we want to put is that LNU should be a location that has not already been used in S. And so the way to say that is just say there's an operator called new lock and takes an argument S, and it returns a location that has not already been mapped in S. So if S is a list of mappings, then LNU is basically a location that does not already exist in S. And that's important, right? We don't want to clobber some existing location. And that's the whole idea, that's the whole notion of declaring a variable. You are declaring an extra region of memory. You don't want to clobber any existing region of memory. And so this is used, LNU is equal to new lock S is used to say that LNU is a location not already mapped in S. And new lock is somewhat like the memory allocation function. You can think of it as the malloc function or the new function, or just a variable declaration is also a way of allocating memory. And new lock is just our way of representing memory allocation. All right. And notice that we don't have any notion of stack, etc. and things like that. Now we are ready to discuss our updated rule for a declaration. So under for a given context S0, the current object, environment E, and store capital S, this expression here, which includes a declaration, evaluates to v2 comma s2 if under the original context you first evaluate E1 to get v1 comma s1, then you allocate a new location in S1. So if, notice that I'm using S1 here, which is the result of executing E1. So all the side effects or allocations caused due to E1 are reflected in S1. And so the LNU is supposed to be a new location disjoint from the locations that were allocated either previously or due to E1. And then you update the environment such that you map ID to this new location, because that's the name of the identifier of the new variable, and you map it to the new location. You map the new location to V1 and you update S1 using that. So environment E is updated using ID to LNU, and S1 is updated from with LNU to V1. And if under this new context E2 evaluates to V2 comma S2, then the whole expression evaluates to v2 comma s2. Now I point out here that this rule, this rule for the semantics of a declaration are almost correct. They are not completely correct. What is the problem? Well, the problem is that at the end of the scope, we just use S2 and recall that S2 contains is just the result of the application of side effects due to E2. But the context in which S2 was evaluated is S1, where LNU has a mapping to V1. So LNU would still continue to have a mapping in S2 because it had a mapping in this part. In the context in which it was evaluated, it had a mapping, LNU had a mapping. So it also has a mapping in S2. And we continue to maintain that mapping even after the scope has ended. So at the end of the scope, S2 still contains a mapping from the newly allocated location LNU. And this is similar to the condition of a memory leak. Ideally, we would have wanted that after the scope is finished, the new location is no longer active and it can be returned. And so, but that's not kind of reflected in this rule. And so this is the situation of a memory leak in our rule. Now the question is, what are the consequences of a memory leak? Well, it depends on what side you want to look at it. For example, one consequence of a memory leak is that, let us say that my store supported only a finite number of locations. For example, if it was a 32-bit memory, then the total number of locations have to be less than or equal to 2 to the power 32. And so if you have a long running program, then these semantics basically at some point will run out of locations, because we are not destroying the locations. And so if, for example, I'm executing a for loop that has this this block in its body, then we are basically creating new locations, but we are never deleting them. And so if a store store S supports only a finite number of locations, we may run out of memory. And that's how we typically think about the adverse effects of memory leaks, which basically means that the new lock operation will fail, and so this rule, this execution operational semantic rule will fail to trigger, and the program will get stuck. Recall that if a program gets stuck, we basically say that the program is incorrect or does not have a well-defined behavior. And so because of this memory leak, even correct programs that actually didn't have a memory leak, if that's what the programmer intended for the semantics of a scope, even correct programs will get rejected because of this buggy rule that we have. So if this rule is actually buggy in the sense that it has a memory leak where it shouldn't have had, then this is a clear consequence. It's a memory leak, and what will happen is it will eventually run out of memory, and even correct programs will start getting rejected. But let's look at it from another perspective. Let's say that this is not an incorrect rule. Let's say this is the intended rule. If this is an intended rule, then incorrect programs may be accepted. So how can that happen? Well, notice that even if you retain L new in S2, then you are basically allowing any expression E3, let's say, after the end of the scope, to potentially cause side effects that potentially mutate the values at location L new. Now, because L new is mapped on S2, it should ideally be correctly mutating that location, and both reading and writing. And so this formulation of a rule kind of allows future expressions that are outside the scope to potentially read and write to the values at L new, because L new still appears to be a valid location. And so if that was not intended by the programming language designer, and if the programming language designer actually wanted that to be a bug, then that's not being reflected in this rule. In fact, from that perspective, incorrect programs may get accepted, because what you really wanted was that if an outside expression E3 accesses L new, then the program should immediately trigger an error or get stuck to indicate that the program was incorrect. But because L new is now getting leaked, we will basically incorrectly accept such a program as correct, and this is another consequence of this buggy rule. And what that means is that it puts an unnecessary burden on the code generator. So typically a code generator would implement such scopes on the stack such that it will allocate memory for this identifier, for example, by decrementing the stack pointer, and then deallocate the memory for this identifier by incrementing the stack pointer back to reclaim the space. But if now the code generator does that, that would not satisfy the rule, because the rule kind of expects that the location L new and its value is preserved, and the code generator is now burdened with having to preserve this L new location either on the stack or on the heap. Now it depends on the code generator what it wants to do, but it puts unnecessary burden on the code generator, and which has also efficiency considerations. So as you can see, like subtle mistakes in the execution semantics have consequences both on the soundness and on the soundness of what these rules represent, in terms of whether correct programs are being accepted and incorrect programs are getting rejected or not. So both of those can get violated, and also it puts an unnecessary burden on the code generator because of this oversight. So here's the correct rule. Here's a final rule that's correct. The only change here is that the final store includes S2, but is S2 minus any mapping for the location L new. So if there, whatever the mapping was for L new should be deleted, and this set minus operator is representing that from S2, and so this represents our final rule for a variable declaration in our programming language.